Chapter 1, we look at functions. Should be mostly reviewed. There's some new notation that you might not be used to. This colon, this is a new function notation for us. This means that f is the function such that x is mapped to 2x plus 3. Or another way to say that is function f such that x converts into f of x. F is the function's name. This is what's going on right here. Set builder notation is the first one here. The set of x's where, the vertical line, x is greater than or equal to 3. The interval notation that means the same thing would be x is an element of, that's what this E curvy looking thing is right here. X is an element of 3 to infinity, inclusive on the 3 side. Now you guys are probably used to writing this as 3 to infinity and then using the parenthetical bracket as opposed to the square bracket. IB uses this reversed square bracket to mean that it's an open-ended interval. It's non-inclusive, whereas the facing inward bracket is an inclusive bracket, equal to 3 but not equal to infinity. So this goofy looking notation that you're going to see throughout the IB text means that x is between a and b. And I suppose technically there should be x is an element of this set, meaning the same thing as this non-inclusive interval. Sign diagrams. This might be something a little bit new. What we're doing is we're looking at the zeros of our graph and we're discussing the behavior on either side of them. So I'm drawing myself a number line labeled with the zeros, and then if the graph is positive, I'm putting a plus. If it's negative, I'm putting a minus. Just like this. This is showing me positive versus negative portions of the graph. Another way that you'll see a sign diagram is to show what's happening near an asymptote. If it's a 0, we put a solid mark on the number line. If it's an asymptote, we put a dashed mark there. Label it with the asymptote value, 0. And then it's negative on the left side, positive on the right side. So here we have a function. We want to draw a sign diagram. Well, the things that go on the sign diagram are the zeros. And the zeros for this function would be where the numerator is equal to 0. That's when x is 1. And also the vertical asymptotes, which is where the denominator equals 0. It's where the function is undefined. So x is equal to negative 1/2. So I'm going to draw my number line. I'm going to put a 1 and a negative 1/2. At negative 1/2 though, remember this is an asymptote, not a value in the function. Now we plug a value in each one of these intervals. So negative 1, if I plug negative 1 in here, we get negative 2 over 1, negative 2. Take that back, positive 2. And then let's plug in 0 is always nice. So 0 minus 1 over 2 times 0 plus 1. And this is just chicken scratch that I'm doing. However you can come up with this is fine. So negative 1 over positive 1. It's negative between negative 1/2 and 1. And then something bigger than 1, so 2. One-fifth, our function is positive there. So this sort of gives us an idea of what the graph should look like. We know that there's an asymptote at -1/2. We know that there's a 0 at +1. And in between those two, the graph is negative. It's positive to the right of 1. And it's positive to the left of the asymptote. A sign diagram can be really helpful when we're solving an inequality that's not the most straightforward, like a quadratic. We subtract 2 to both sides. 3x squared plus 5x minus 2. And what I'm going to do is I'm just going to treat this like it's an equation. I'm going to find the spots where this does equal 0, and I'm going to use a sign diagram to help me straighten out which intervals will actually work. However you go about solving this quadratic is fine, but this is factorable. 3x minus 1 and x plus 2. So x is equal to 1/3 or -2. So I'm going to come over and I'm going to make myself a small sign diagram. These are both zeros of the left-hand side. I want to know where is this going to be greater than or equal to 0. I want to find the positive intervals. I'm going to start out by plugging in 0. 0 plus 0 minus 2, that is negative. That's less than 0. And there's a nice property that they mention in the book, and that's if a factor has an odd power, there is a sign change about that critical value. So -2 came from the x plus 2 factor. That x plus 2 factor has an odd power. It's to the first, which means that at the critical value of -2 there's a sign change. If it would have been x plus 2 quantity squared, then it would be negative on both sides of that critical value. And the other nice thing is I don't have to test any other values because 3x minus 1, that has an odd power too, so there's going to be a sign change at 1/3. So my solution here x is an element of -infinity to -2 inclusive union with 1/3 to +infinity non-inclusive. Or in set builder notation, the set of x's where x is less than or equal to -2, or x is greater than or equal to 1/3. Either notation is just fine to use. Here's another inequality. We want to solve this. Now what I'm going to do, I'm going to make this equal to 0. I want to be careful not to cross multiply because it's real easy to forget about the fact that there is a value that makes this undefined. So I'm going to go ahead and leave that into this problem. You can do it that way, but I don't really recommend it. I'm going to subtract 1 from both sides. I get 3x plus 2 over x minus 4 minus, I'm going to go ahead and get a common denominator right now. And I now have this being less than or equal to 0. And now I can combine like terms on the top. 2x plus 6 over x minus 4. We have a 0 at negative 3 for x, and a vertical asymptote at x equals 4. All the joys of recording in the summer when all the dogs are out in their barking glory. My dogs and neighbor dogs. Huzzah! So sign diagram. We have a vertical asymptote at 4. We have a 0 at negative 3. And I'm going to come back to the original function to plug, not the original function, I'm going to plug in, say, 0. So we have 6 over negative 4. That is a negative number. The 2x plus 6, there will be a sign change there because that's an odd-powered factor. And then the x minus 4 is an odd-powered factor, so we should have a sign change here. If we're not sure, we can always double check. Pick 5. 16 over 1 is a positive number. So my solution is that x is an element of negative 3 inclusive to 4 exclusive. And as you're using this interval notation, I would really recommend that you try to use the IB's notation. Just because you are going to see that, you do need to get used to it, and you probably should use it when you're taking their exams. The modulus, absolute value. Remember, absolute value means distance from 0. So this stuff in here has a distance from 0 of 4, which means that stuff can either be 4 or that stuff can be negative 4, and this equation will hold. To solve this, we're going to multiply by 1 minus x. Get all of our x's to one side, our constants to the other. X is 2/7. And we really should go back and check, because this is a rational function, does the denominator become 0 by having this as a solution? And no, it doesn't. And then we take the second one. We're going to multiply by 1 minus x again. Variables to one side, constants to the other, we end up with x equals 6. And that also doesn't give us a 0 in the denominator. These are both solutions. An absolute value inequality, if an absolute value is less than a number, then what we're going to say is that x has to be between k and negative k. If that number has to be a distance less than 5, that number has to be between 5 and negative 5. If the absolute value is greater than a number, then x either has to be greater than the number, or x could be less than the opposite of that number. And both of these statements hold for less than or equal to, greater than or equal to. So to solve an absolute value inequality, the first step to do is to rewrite it here. With an absolute value equation, first thing to do, the way we get rid of the absolute value, is we rewrite it as two statements. An inequality is no different. To get rid of the absolute value symbol, we have to rewrite the inequality in one of these two ways. Asymptotes. We're going to look at this function, function g, that takes x and maps it to this. And before we look at the asymptotes of that, let's look at what gives us an asymptote. Horizontal asymptote occurs when the limit of the function as x goes to infinity is equal to a number. And that value, k, would be our horizontal asymptote. A vertical asymptote occurs when the function is undefined. And an oblique asymptote or slant asymptote occurs when the limit of f of x as x goes to infinity is equal to some other function of x. This occurs when the degree of the numerator is 1 more than the denominator. We'll either have a horizontal asymptote or an oblique asymptote with a rational function, but we'll never have both. It'll be one or the other. So let's take a step back to this previous example, this function g. So we want to know where the asymptotes of this are and what they are. Well, starting with the vertical asymptote. Can x squared plus 1 ever equal 0? And you should be thinking, no, it can't. So there is no vertical asymptote. Now, to find out if there is a horizontal or an oblique asymptote, I can look at this and tell you right now that it's going to have an oblique asymptote, because the limit as x goes to infinity of g of x is equal to 2x. So the oblique asymptote is y equals 2x. I know that because this last term, if I divide everything by x squared, we end up with 0 over 1. So as x goes to infinity, this last remainder part, if you will, becomes 0 as x gets infinitely large. So we're left with 2 times whatever the x value is. Now another way to look at this would be to take this whole thing and combine it together. So I get a common denominator. I would distribute I get 2x cubed over x squared plus 1. What I now do, another way to get this asymptote, is to do long division. So 2x cubed on the inside and then x squared plus 0x plus 1 on the outside. And now we go through this long division process. I get 2x, that would give me 2x cubed plus 0x squared plus 2x. I'm going to subtract the two lines. And since x squared can't become 2x, this is my remainder. Which was my original function. And that will always be our oblique asymptote. The remainder becomes negligible because x is bigger in the denominator. So as the limit goes out to infinity, we end up with 0 for that remainder. A little bit more terminology. A function is one-to-one if it satisfies the vertical line test and the horizontal line test. What that means is that every x is paired up with exactly one y, and every y is paired up with exactly one x. An easy way to see this is to draw a mapping diagram. 1, 2, and 3 are my x's. 2 and 5 are my y's. And although this does represent a function, it does not represent a one-to-one function. It would pass the vertical line test just fine. But when we look the other way, the output of 2 is paired up with 2 inputs, so it's not one-to-one. The second relation for every x there is only one y, and for every y there is only one x. This second function is one-to-one. It passes the horizontal and vertical line test, and as a result, that second function would also have an inverse that is a function. The first function, its inverse, is not considered a function. Its inverse would not pass the vertical line test. So you should be working on problems. If you come across any that you have issues with, please feel free to let me know, and I'll help you out as best I can.